Thank you, everyone. I'm Ted from Wiwynn. Today here, we want to talk about data analysis for manufacturing test results for DRAM module. Okay. What does Wiwynn does in the past? We have labs design some OCP machines. We have a factory to build the systems. At that factory, we have lots of test software in the manufacturing procedure. Then those systems will move to their customer's data center through some monitoring procedure. Okay, in that manufacturing process, we get lots of billions of test log entry every year. So how can we do for that data to improve our performance? Data analysis, we can go back to provide a better design for good MTF, MTBF, and we can enhance our management software for best serviceability, and we also optimize the procedure in our manufacturing. Okay. Next one, I will show you guys some information about the failure rates with the different DIMM modules in our manufacturing procedure. We're just a system building company, so we got a DIMM module from our vendors. We build a system, and before we ship the racks to our customer, we do some stress tests, then get some failure rate to fill out the defect rates. So as you see in the table, the 32 gigabytes DRAM will get a little higher defect rate than other size. Well, that's obvious. That's clear. Why? Because we do some stress test. If any rewrite byte get errors, the DIMM module should be identified as a failure one. So 32 gigabyte will get higher defect rate. We have three major vendors. You can see their failure rate is around 0.6% to around 15%. Yeah, that's the average ratio we get in the past year. The next one will be a flash. We use DRAM, then we test the flash storage. Over 700K modules in the past few months. You can see the failure rate just around 0.1%. Okay, for those 5 vendors. Another one is hard drive. Okay, there's the last major component we test. Over 2 million hard drives. And you can see the failure rate is a little just lower than flash and DRAM. Okay, we have 3 major customers. Okay, vendors. For that 3 major parts, we decide to study and research for DRAM first, because for DRAM we got lots of feedback from our customer about their reliability. Reliability of engineering of DRAM, we got great compact and difficult to control in production test. Why? The first, it's difficult to define the golden testing time. How much time we have to test for the DRAM module? 24 hours, 72 hours. How much time we can identify that this DRAM is good under the stress tester environment. The second one is how to define the error threshold in the testing time. It's still an open problem. The more higher or lower strategy will get a different result for our testing cost. So we want to try to find the trade-off value to get a better performance. The third one is In the current manufacturing testing, we sometimes we need several testing time to identify, to make sure the DRAM is failed, because the test results affected by different environment parameters. For example, the DRAM module did not be plugged safely in the socket, right? Even it's good. So for the stress test process for DIMM, according to the right side of the picture, the hot top curve as your reference, we will focus on the left part in the beginning. If the DRAM module can pass the stress test, then we can identify it's good. It can use in our customer's environment. So we use the utility from Google, the stress test APP test version 1.0.3. Yeah, that's why. That's the utility. It's open source we used to test the DRAM. Our testing model, okay. Finally, we used to check any ECC error occurred to identify the DRAM module is good. We define the testing time will be the TD, so as I say, how much time we have to test is a TD. Then, if we get the ECC error occurred exceed the Emax, that's the upper threshold. If we find the DRAM module get ECC error more than, there's a correctable, okay, single bit error, more than the threshold, that DRAM module will be identified as a failed. The next one is no uncorrectable. That means no multiple bit error happen. If anyone happen for the DRAM, they will be failed. So according to the model, we collect a data set in our manufacturing process. We use 80K DIMM modules, those installed in the 10K system in a limited time period. Just about 2 months we produce. We do build lots of machines, but we just focus on the certain 2 months data. The basic things we find is the quality, DIMM quality about at least one ECC error occur in the testing. You will see there's around 0.5%. Okay, so that means at least around 50 modules in 1,000 DIMMs will have at least one ECC error occurred. So you can see the data observation. We collect the data and try to find out the first ECC time occurred time. You will see the beta means the 80%, and the alpha will be 90% to be covered. So in this map, the testing time will be normalized as 10,000 normalized units. Okay, you will see just around 440 normalized time, up to 90% DRAM will have their first ECC error. So according to the graph, you can see we can focus the testing procedure on the first half testing time to identify the defect. We normalize the total testing time to 10,000 time units. Okay, for the analysis can be more simplified. At least one ECC error in testing, and you can see, as I say, 80% coverage will be around 300, and 90% will be 440. Then we go to the threshold. So there's an Emax, what I mean that Emax is a threshold number. For example, 5 or 6 numbers the segment distribution between the first one and the Emacs will be shown like this. You still can see lots of DRAM, lots of ECC error occurred in the beginning. Okay, we only showed about 25 normalized time in this picture. Then we find something. We use some average linkage method to analyze what is the, do we find any special type of DRAM errors? After this analysis, we find lots of error occurs between 3.5 normalized unit. We call it a bucket. That means if when the DRAM under the test, if the first ECC error occurred, some kind of DRAM module will get another and more ECC error happen in the later period. So if we define, if those, if a DRAM, there are more than threshold, that means Emacs, ECC errors happened in this 3.5 normalized time, we call it is a spike. Okay, it's a spike. Another type is sparse. We define there's their ECC error occurrence is more sparse. Okay, it's more random. It cannot be centralized in a certain of time. Okay, and then according to our calculation and analysis, the ratio for spike and sparse just only half-half, so around 50 for spike and 50 for sparse. Well, then how do we treat to assess those things? In this graph, the spike, we focus on spike first. Spike, those data just for the defect RAM we pick up from those data. Through the Weibo distribution, the first ECC error, the distribution just like that. You can see it's just around 500 for the 80% coverage and 700 for 90% coverage. Okay, you can see that. So according to the graph, the picture, you can see for the spike assessment, around the 750 time units, 90% coverage will happen, right? And that is a sparse assessment. Okay, it's a comparison to spike. The distribution will move to later around 100 time units. Okay, so that means you need more time to identify the defect DRAM module if the module is a sparse type. Okay, I'll give you a table later to compare them. So our purpose, okay. So I'll give you some calculated and analysis data. So our purpose is shorten the testing time, but still maintain the quality. How can we do for those data? Okay, it's straightforward to just cut the testing time and raise the threshold as compensation. You think, I don't want to spend a whole 72 hours or the whole 3 days to test the DRAM. Can we just test in only 1 day or 1 or 2 days? Okay, but at the same time, you have to change your threshold, maybe more with a more rigid threshold to fill out the DRAM module. However, the benefit of less test time will be offset by less error coverage. Okay, you shorten your testing time. Then I believe there must be lots of DRAM cannot be cached, cannot be figured out, and there are some DRAM will be identified. Will be some normal DRAM module will be identified as a failed. It's a false alarm. Okay, so we want to find out a solution to compensate those conditions. Okay, that's our criterion. Okay, testing time, threshold, catch rate. Catch rate means you have original data you get by the old rule. Then we change the rule. The new data divided by the old data, there's a catch rate. Okay, and the false alarm, there's a good. The good one will be recognized as the bad one by the new criteria. So after that, 3 steps to analysis. Okay, we use 80K modules as a trend data. Okay, we do the first direct data verification, try to find any relationship between those parameters, and we use the Weibo distribution to predict criteria. As the curve you see on the figure, it can to predict the correct parameter we can use. And finally, we use the new data. Okay, we use the data from maybe 2 months before that. We use another data in the different months to do the cross verification. Okay, so we have the trend data, we have the predict criterion, then we have new data to cross verify. This just for your reference, the data used for cross verification is still similar to the trend data. Okay, the basic error rate is similar, right? Okay, that's very important. Otherwise, if we use the new data with the very bad quality DRAM, the result will get some wrong direction. Finally, it's a table, we got it. For direct verification data, if you want to get a catch rate around 90%, then your testing time can be reduced from TD to only 3/4. That means then your error threshold must be set as half of the original. For example, if you use the Emacs as a 6 ECC error, if there are 6 ECC errors happen, that you will kick out the DRAM module. In this formula, you can use only 3. So the time is shortened, the threshold is more rigid. Then you got a false alarm. Okay, there's some good DRAM module will be recognized as a bad one. At this time, it's around 0.16%. Okay, it's not so bad, right? Then for 80% catch time, the catch rate 80%. Okay, 80% maybe is acceptable or not. It's just by a customer. The testing time can reduce to only half. So you can have only half testing time and 1/3 threshold. Then you get a little higher false alarm. Yeah, that's our direct verification. Then through the cross verification data, you can see you still get a similar result. So we have trend data to get the testing time and the new ECC error threshold, and we use the new data to cross verification, then get a similar result. So yeah, maybe we can consider in the future the testing time in Wiwynn maybe can be shortened to 3/4 or maybe half. So we don't need to 72 hours to test. We only need maybe 36 hours that we can finish the testing. Yeah. So how do we get, what kind of benefit we get? Shorter time, more capacity to produce at a lower cost. Yeah. But we also have some false alarm there, so it still has to be treated. Okay. So we build the cost response model, not just the number we show there. There are some elements of the cost response model. The first one is the cost with the catch rate. Okay, if the catch rate is not high enough, you get the RMA cost because those things should be filled out, and then you move to customer. There will be return. So there's RMA cost. Another is operation loss for external customer. Your customer get those DRAM to get defect, and he cannot operate normally, so get some operation loss. The third one is reputation. Well, shame on you. How can you test so bad like that? So the reputation should also be counted as the major issue. Another one is, as I said before, there is some false alarm rate. How can we handle that? There is additional cost. We have to test it again. The third one is we do shorten the testing time, so the test cost, the MOH will be reduced. Okay. So there's some combination, and we try to figure out how much we can improve by those models. Okay. So conclusion is we just analyze those events from manufacturing data, and we try to produce a model, okay, to find anything we can do. In the future, we will move to Flash first, try to find any possibility to improve our production test for Flash parts, then the hard drive maybe, okay. All right, we have a white paper available now. So if you want to take a look more detailed, you can have your link. It's a QR code. You can take it, and you can get a white paper from the Wiwynn's web. Yeah. So any questions? Yeah.
Testing every single memory during process, or it's just for your qualification?
We test every DRAM module installed in our system.
So, okay. So during boot process, you basically run your memory self-test.
Yes.
That's the data you're getting.
Yes.
Not extensive qualification process.
No.
But how can you do 72 hours with just test memory for your regular testing?
We in the manufacturing, we test and deliver at the rack level. So we build the whole rack for some spec, some type of combination. Every server got lots of memories, right? We run the memory test program to test every single memory module.
Just for that one, you do 72 hours, so the whole server testing would be a lot longer, right?
Yeah, there's a lot of testing running at the same time.
I see, got it.
Right, so some testing tool will test the NIC card or hard drive. They are running at the same time. So right now it's 72 hours. Okay,
so you run 72 hours, your data is based on your specific memory test module.
Yes.
At the same time, other tests were doing as well.
Yeah, that's right.
All right, thank you.
Okay.
So as for your predictive analytics, you already assume that it follows the specific distribution, right? I mean, you did not try to look for any or discover any distribution statistically. You assume a model.
Okay,
right?
According to those data, we try to different formula or different distribution models try to approach those data. We find this one we choose is the best fit those data. Yeah, of course, you can choose like a log normal distribution. They can predict, okay, we did predict like use the log normal distribution, then generated the very similar parameters as you see now. So that's the best two approach we can use right now, according to the distribution.
Okay, and in your cross-validation or cross-verification, you just took like one chunk, or you just took like random chunks from the cross-verification and tried to do a fit your distribution?
Okay, according to our model, the trend data and the cross-verified data are different part. In some modeling, they use the part of the trend data go back to verify, right? But for us, well, that's a good way. But for us, we try to prove our predict model is good. So I choose to use the bigger cross verification data, because we get those data from the same production line, just maybe in a different time, only few months difference. So I believe it should at the same condition. Yeah. So through the cross verification data, we prove, well, the predict model generated some correct parameters we can use, right? Yeah. It's all right? Okay. So any question? No? Okay, great. Thank you, guys.
Thank you, Ted.
Thank you.